Hello everyone. Through this video, we are going to discuss about some basic concepts of permutations, like some theorems and all, which are essential for proceeding with the exercises. So first, let us look at the definition of permutations. What do we have here? The statement of the definition can be put forward in this way. Each of the arrangements which can be made by taking some or all of a number of things is called as permutation. So this is the definition of permutation. Now with an example, let us proceed with. Say this is the example. The example is what? Suppose a three-digit number is to be formed from using digits 0 to 9, okay, without repetition. So here in this case, total number of digits given is 0 to 9. That means 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So in total, how many digits do we have here? In total, there are 10 digits. We have to make a 3-digit number. We have to construct a 3-digit number using this 10 digits. So what shall I do here? See, this is the actually I have to construct 3-digit number. Say this is hundreds place, this is tens place, and this is ones place. We all know one thing, that if in case of a 3-digit number, in the first place, I mean in hundreds place, if I put 0, then it will ultimately become a 2-digit number, because in hundreds place of a 3-digit number, if 0 is put, it is meaningless. So ultimately it will imply a 2-digit number. So here in this case, apart from 2, the rest of the numbers we can use. So there are 9 possible ways of putting the digits in the place of 100. Now if one number out of these 10 digits is put here, actually out of 9 digits, there should be 9 options for this hundreds place. For hundreds place, out of 9 options, if I put any one option here, how many options will be left in our hand? In total there were 10 digits, so out of which I have already used one option here. So how many will be left in my hand? There will be 9 options left. So for this position, what I shall be doing, from total of 9 remaining options, I shall be choosing 2 digits. Means here in this place there will be 9 options, means any one of these 9 options I can use here, and then from the remaining 8 options I can use any one here. So in its place one option, and in its place another one option I have to put, respectively from 9 remaining options for tens place and 8 remaining options for ones place. So in terms of permutation, how can it be framed? Let us check below. First of all, we have to proceed with the notation. How permutation is denoted. Notation. So for this part also there is a statement: if small n and small r are positive integers such that I can write here 1 is less than r, less than equal to r. Here also r is less than equal to n. Then the number of all permutations, means all arrangements. In my very first video already I explained this. Arrangements means that actually refer to permutations. All permutations of small n number of distinct things, n distinct things taken r at a time. Taken means out of n distinct things we have to take r at a time. Taken r at a time is denoted by the symbol P N R, or we can write like this, NPR. Actually it is read as PNR. Okay, permutation of N and R. So just below this I am going to write away, thus PNR is equal to total number of permutations of n distinct things taken r at a time. Let us come back to the previous example now. In this case, what I told you, in this last two places I have in my hand 9 options left, out of which actually out of 10 options already one option I had taken for the hundreds place. So from the remaining 9 options in my hand I have to select, I have to choose 2 options for these 2 places. So in terms of permutation this can be written in what way? The way of writing this is, out of 9 options in my hand I have to take out 2 options. So it can be written in the form P92, and that's the way these things can be represented in terms of permutation. I hope all of you have understood. So till now we have done notation. Then after we shall be dealing with the first theorem, which will be important for proceeding with the questions of permutations. The first theorem, the statement I am going to give you here, the statement is this. This is theorem 1. If small n and small r are positive integers such that 1 less than equal to r less than equal to n, then the number of all permutations number of all permutations of n distinct things taken r at a time is given by capital P n r. This stands for what? Permutation of n selected r at a time is equal to n into n minus 1. Sorry, it should be cancelled out. N minus 1 into n minus 2, then after n minus 3, it will be going on up to n minus r minus 1 whole. So coming to the proof part, let us check here. This is the statement. So when we come to the proof part, first of all we should be clear about one thing, that here in this case total number of things provided is n, out of which we have to select r at a time. So here in this case what we shall be doing, first of all I shall mention that total number of distinct things is equal to n. Number of things to be selected at a time is equal to r. Now what does it mean? This actually means that we are to fill in r number of boxes using these n number of things without repetition. So how can it be done? Let us try to make r number of boxes. Since we do not know what is the value of r, therefore of course this is the way we have to frame the boxes, yes or no. Like 3 boxes I made in this side, and at last 2 boxes I made. Okay, so this is the first one, this is second one, this is the third one, and then this is rth box, this is of course r minus 1 box. So in the first place, how many options are total number of objects, total number of distinct things we have as n, yes or no? So possible number of ways to fill up the first place will of course be n. The number which is used in the first place we do not have to repeat in the second place. So how many options are there in my hand left? Of course n minus 1 options for the second place. Then for the third place we are having the options left is n minus 2. Now one thing we have to notice, that in the second place I am writing minus 1. In the third place I am writing minus 2. That means depending on the position of the box, the term written here is 1 less, yes or no? That means in the first position, I'll repeat it again, in the first position for place 1, I can write here simply n. N stands for what? N minus 0. Then for the second place, I am writing here n minus 1, means the number of, the position is 2 here, but number subtracted here is 1. That means that is 1 less than the position number. Then in the third place, position of this place is 3, but the number I am subtracting is 2. The same thing will continue here also. Means in this place, the position is r minus 1. So the number to be subtracted here should be what? It should be 1 less than this one, means r minus 2. Means like this we need to write n minus r minus 2. Then only it will be balanced. So here in this case, in the rth position, it will be of course n minus r minus 1. So all these r positions are required. We cannot ignore any one of the boxes. Therefore, the term and should be used in between. Actually, I am going to use here fundamental principle of counting. That also the fundamental principle of multiplication. Why multiplication? Because I have to consider first place and second place and third place, and there is a continuation up to rth place. Means there will be and in between the boxes. Therefore, by fundamental principle of multiplication, total number of permutations will be equal to n into n minus 1 into n minus 2. There will be continuation up to n minus r minus 1. So this can further be written as PNR. That also can be written as PNR is equal to n into n minus 1 into n minus 2 continuation up to n minus r minus 1. And that is how it can be proved. Hence, proved. So on the basis of this theorem, the second theorem can further be proved. Let us check how can it be done. So I am going to write here the statement of theorem 2. So here goes theorem 2. Theorem 2. So the statement is like this: prove that, and this theorem is very important, prove that PNR, or you can write this in this form also, is equal to n factorial. The concept of factorial already we have learned in my last video. So n factorial divided by n minus r factorial. Now let us check the proof part. Just now we have learned that we know that we can write here, we know that PNR is equal to n into n minus 1 into n minus 2 into, there is a continuation of n minus r minus 1. So this formula, this statement already we got just now. So after this, what can we do? If we notice the left hand side, actually this we can perform the role of left hand side in this statement, because this is the left hand side here. So LHS, in the LHS what I am writing, PNR, that can further be written as this is the form I am going to write here next, n into n minus 1 into n minus 2 continuation up to n minus r minus 1. But the term that will come after this n minus r minus 1 is what? It is n minus r. Yes or no? After n plus r, n minus r, what term comes? Of course r. So then after, what term will come? R plus 1, and gradually we are going to get these terms. Now if I am putting these components, I mean these factors, from my side it has to be balanced further in the denominator part also. Means I am going to write in the denominator part these terms, continuation up to 3 to 1. Means in other words, I am multiplying both numerator and denominator by the term n minus r into n minus r plus 1, continuation up to 3 into 2 into 1. So why we are doing this? Because if I write this with continuation up to 3, 2 and 1, I can get the result for n factorial. Yes or no? Because for n factorial, the result is what? N into n minus 1 into n minus 2 into n minus 3, continuation up to with lots of terms in between, and continuation up to 3, 2, 1 as the last terms. Therefore, with an intention to get n factorial, I had to multiply both numerator and denominator with those terms what are not present with the numerator part initially. So after this, I can reduce this step into the form of the numerator as n factorial and the denominator as what? N minus r. Then if it continues up to 3, 2 and 1, then ultimately this will give us the factorial of n minus r. And this is the required right hand side. So this is the right hand side. Hence proved. This is the second important theorem. Coming to theorem 3, the third important theorem. Theorem 3. The statement is what? The number of all permutations of n distinct things taken all at a time. Here it is what? Taken all, not taken r. Taken all at a time is n factorial. So coming to the proof part, we already know that, means the first theorem I want to state once again. We know that P n r is equal to n into n minus 1, n minus 2, continuation up to n minus r minus 1. Yes or no? In the first theorem only I got it. So coming to the next steps, let us first delete this part. It should be r minus 1. When taken all at a time, of course we have to write what? Then r is equal to n. Yes or no? Because the permutation of n distinct things taken r at a time is this one. But the permutation of n distinct things when taken all at a time, that will imply what? R is equal to n. Means all the numbers, all the distinct numbers I am taking, or all the distinct things I need to consider there. So in this case, in number 1, say this is expression 1. So 1 it will imply as what? P n comma n is equal to, what can we write here? N into n minus 1 into n minus 2. There is a continuation up to n minus, in place of r, what do I put here? N minus 1. Okay. So after this, what shall I get? p n comma n. This will give us n into n minus 1 into n minus 2, continuation up to when I remove the inner brackets, n minus 1 will be getting cancelled, n minus n will be getting cancelled, and minus into minus, it will turn positive 1. Okay, so before this, of course, I am going to get 2, yes or no. So ultimately this will give us the result of n factorial. From the expression itself, it is very clear, n factorial, yes or no. So the result comes as p n means permutation of n distinct things taken n at a time is n factorial. So this is the proof of theorem 3, hence proved. So next we shall come to theorem 4. So here goes theorem 4. Theorem 4, this is another important theorem. Somewhere it is asked also. 0 factorial is always equal to 1. 0 factorial is always equal to 1. So coming to the proof part, we know that p n r is equal to n factorial divided by n minus r whole factorial. So if we consider when r is equal to n, then it will become p n comma n is equal to n factorial by n minus n factorial, putting n in place of r. This implies in the previous theorem, I mean in theorem 3, already we got that p n of n is equal to n factorial. So that we can substitute here in this place, like n factorial is equal to n factorial by 0 factorial. So when we perform cross multiplication, it will be like 0 factorial into n factorial is equal to n factorial. So n factorial on both the sides got cancelled, resulting into 0 factorial is equal to 1. So this thing is to be remembered for further calculations. It's very important. So hence proved. This is an important result. So with this, I am going to discuss 2 more questions actually after these theorems. Let us come to the first question. The first question is what? Question number 1. What is said here? If 2 into p 5 comma 3 is equal to p n comma 4, find n. So coming to the proof part, I mean solution part, we have the given statement, I mean given expression only I am going to write here. The formula is already known to you now, n comma 4. So here I can write 2 into, using the formula of permutation like this, p n comma r is equal to n factorial divided by n minus r factorial. So this formula I shall be using here. So how can it be used? 5 factorial divided by 5 minus 3 factorial is equal to, in the same cases here, n factorial divided by n minus 4 factorial. So we can write further 2 into 5 into 4 into 3 into 2 factorial. I kept here 2 factorial. I stopped here at 2 factorial because in the denominator also I am going to get 2 factorial. So both these two terms will be getting cancelled. On the other side it will be n into n minus 1 into n minus 2 into n minus 3 into n minus 4 factorial, and the denominator is n minus 4 factorial. So I stopped at n minus 4 factorial in the numerator part. So these two got cancelled and I got the result here to be ultimately I can write this as 5 into 4 into 3 into 2 coming in the descending order, and on the other side n into n minus 1 into n minus 2 into n minus 3. Now if I want to follow this format on the left hand side also, what can we do? 5 minus 1, 5 minus 2, then after 5 minus 3, and that way it will go on. One correction I have to make here, this will be deleted. And I put here 1. So n minus 1, n minus 2, n minus 3. So comparing both the sides, I shall get, means if you notice, you will find that first place is n stands for 5. Again in the second part n minus 1, here I am getting 5 minus 1, so n can be considered as 5 also. So after that in the third part I am getting n minus 2, while on this left hand side it is 5 minus 2. So everywhere where there is n, there could be 5. Therefore comparing both the sides I get n as 5, and this is the answer. If I go for solving both the sides, it will be taking lots of time, yes or no. Therefore comparing both the sides, this can be evaluated very easily and comfortably. So coming to another question, this is your question number 2. The question is, if P 5 comma r is equal to 2 into P 6 comma r minus 1, find r. So coming to the solution part, what can I write? We have P 5 comma r is equal to 2 into P 6 comma r minus 1, using the formula for permutation, like 5 factorial divided by 5 minus r factorial is equal to 2 into 6 factorial by 6 minus r minus 1 whole factorial. Which formula I am using here? P n comma r is equal to n factorial by n minus r factorial. So this is the formula used here. So after this, what can I write? I can write here 5 factorial divided by 5 minus r factorial is equal to 2 into 6 can be written as 6 into 5 factorial, so that on both sides 5 factorial gets cancelled. And then after, what do I get? 6 minus r plus 1 factorial. So after this I shall write 1 by 5 minus r factorial is equal to 2 into 6 divided by 7 minus r factorial. After that, if I want to proceed with further cancellation, let us do this in this way. 7 minus r factorial I carried to this side, then I kept here 5 minus r factorial, that is equal to 2 into 6. So if I break this factorial notation in the numerator part to the descending order, I can put here 7 minus r into, then again 6 minus r means one term less than the first one, into 5 minus r factorial. I stopped here so that cancellation can be done with the denominator, and I got here the term 12. Now one thing can be noticed here, that on the left hand side, whatever numerator we are having, these two terms are consecutive terms, 7 minus r into 6 minus r. So let us break this term into consecutive terms, factors of two consecutive terms. So I can write here 4 into 3, yes or no? So 7 minus r into 6 minus r. If I try to arrange these two terms in the form of these two, it will be 7 minus 3 in place of 4 and 6 minus 3 in place of 3. So comparing both the sides, what do I get? 7 minus r, here on the side 7 minus 3 means 3 is taking place of r, while on the other side 6 minus r means 6 minus 3. So comparing both the sides like the previous sum, I can write here, comparing both the sides, I get here r is equal to 3, and this is the answer. So these are some preliminary concepts of permutation which we discussed today, along with two simple questions. In my next video, some more questions we shall be discussing. Thank you.